Convex optimization is extremely important to lots of different parts of machine learning. It's one of the few kinds of optimization in which we not only have guarantees on getting a good result, but also how long it might take to get that result. As with other videos in this series, I'm not going to attempt to get into real details on convex optimization, but really just give you some of the highlights and explain some of the terminology. Convex optimization is an active area of research. There are some great review papers to check out and also several great books. I'll point in particular to the classic by Boyd and Vandenberg. To get started, let's talk about the idea of a convex combination. If I have two kinds of objects for which addition and scalar multiplication are defined, then a convex combination sort of blends them together. In a convex sum, I weight the two objects in such a way that the weighting adds up to 1. Typically, I would have the weight be a number between 0 and 1, denoted here as alpha, and then the other weight is 1 minus alpha. A convex set is then a set of objects in which if I take any pair of the objects and form a convex sum, then that new object is also in the set. That is, the set is closed under convex combination. If you think about it geometrically in RD, then a convex set is a set such that if I draw a line segment connecting any 2 points in the set, then that whole segment is also in the set. Another way to think about it is that convex sets are the kinds of shapes that don't have any dents in them. On the right is a set that is not convex because it's possible to draw a line segment that leaves the boundary of the shape. That is, it's not closed under convex combination. Convex sets have some very nice properties that are worth going over. One basic thing to know is that the empty set and, of course, all of RD are both convex sets. The convexity of a set is preserved by scaling and translation. In fact, more generally, the image of a convex set under an affine transformation is also a convex set. Very important for convex optimization is the fact that intersections of convex sets are also convex. This makes it possible to combine different convex constraints in a single optimization problem. Notably, things like hyperplanes and half spaces are also convex sets. These form the basis for a lot of practical convex optimization problems. This leads us to the idea of a convex function. On the left-hand side here, we have a function that is applied to a convex combination of inputs. And on the right-hand side, we have a convex combination of the function values at those inputs. If the function is convex, then the left-hand side will never be bigger than the right-hand side. A strictly convex function also disallows equality when x1 is not equal to x2. Although this sounds like a bit of a technical definition, it's pretty easy to understand. Convex functions have the property that if I take any chord between 2 points on the function, it's always above the function. Here are some useful properties to know about convex functions. The first one is a biggie for optimization, which is that any local minimum is also a global minimum. The second property is that when the function is twice differentiable, the Hessian matrix is always positive semi-definite. You can think of this as meaning that locally, a convex function is always kind of like a quadratic bowl. It's also useful to know that level sets of a convex function are convex sets themselves. Note that the converse is not true. If all the level sets of a function are convex, that does not mean that the function is convex. Another useful property is if I take a convex function and multiply it by a positive constant, then it is still a convex function. Similarly, the sum of two convex functions is also a convex function. Also, the max of two convex functions is a convex function. These last two properties might be a little bit tough to see, so I've made a visualization. Here are two convex functions shown in orange and blue. Now in green is the average of the two functions, that is a scaled sum. Note that this function is also convex. Now I'm showing the pointwise maximum of the two functions in purple. Note that it is also convex. Now with those ideas established, let's talk about optimization. Most generally here, we're thinking about optimization under constraints. We require that the overall objective function and the inequality constraints be expressed by convex functions. Any equality constraints must be affine. Constraints of this form define a convex set. Combining that with a convex objective function ensures that all local minima are global minima. There's a lot of different terminology in convex optimization, and it can be difficult to keep track of it. Part of this confusion is because convex optimization is sort of claimed by several different mathematical subfields. But here are some terms that are pretty consistent. The input vector to the function is called the optimization variable. The function that we're trying to minimize, f0, is the objective function, or sometimes called the cost function. The other functions I'm denoting here with f are the inequality constraints. The functions I'm denoting here with h are the equality constraints. The set of points that satisfy the constraints is the feasible set. The optimal value of the function is then the minimum within the image of the feasible set. An optimal point is a member of the feasible set that achieves the optimal value. At some point x, if one of the inequality constraints is 0, then we refer to that constraint as being active. You can think of active constraints as the ones that are actually pushing against the value. Inactive constraints have a function value that is strictly less than 0. An inactive constraint at the optimal point wouldn't change the optimal point or the optimal value if it was a little bit different. So why do we care so much about convex optimization? Well, there's a lot to like. First, it turns out that a lot of different kinds of problems can be framed as convex optimization problems. That is, it's a pretty big toolkit for solving lots of different kinds of machine learning and operations research problems. Also, convex optimization is generally repeatable. If two people solve the same problem in different ways, they're still likely to get the same answer. This is important for science, but also for various kinds of business decisions. Additionally, we care about the computational complexity of optimization problems, and many convex problems can be solved in polynomial time. Finally, when a convex optimization problem is framed in a standard form, there are often pretty good software packages for solving it in an off-the-shelf way. Now, the downside of convex optimization is that not everything we want to do can be framed as a convex optimization problem. In particular, things like deep neural networks and Bayesian inference tend not to have convex objectives. One of the reasons we like convex optimization is also because of the concept of duality. You can think of this as a kind of transformation from one optimization problem to another related optimization problem. Sometimes that problem is easier to solve. On well-behaved convex optimization problems, the solution to the dual is also the solution to the original problem. With the dual, we have a bigger toolkit for solving these difficult problems. Our starting point for talking about duality is to talk about the max-min inequality, which is an inequality that is true for any function of two arguments. All it says is that the maximum over one variable of the minimum over the other variable is never larger than doing it the other way around. That is, the max of the min can't be larger than the min of the max. The proof is not too hard. First, imagine fixing x to some x prime. Clearly, the min over y is less than or equal to all of the other values of the function for other y's. That's true no matter what x prime we choose. So if that's true pointwise for any x prime, then of course it's also true at the max. And if that's true for any y prime, then it's also true at the min, and we're done. Let's try to get a sense of what's going on here visually. Here's a big grid of points that's approximating a smooth function. The darker areas have lower function values. Now let's go over each row and mark the square that has the minimum value in each row. Then let's mark the square that has the largest value over all of the squares we just marked. So that's the max of the min of each row. Now let's go over each column and mark the square that has the maximum value in that column. Now let's take the smallest one of those, that is the min of the maxes. Now the point here is that the min of the maxima is going to be larger than the max of the minima. Let's see how this comes up in constrained optimization. Here's a little bit simpler version of the problem that we looked at earlier with no equality constraints. We could introduce Lagrange multipliers for the constraints and write down the Lagrangian. I'll denote the Lagrange multipliers as lambda, and so the Lagrangian takes two arguments, x and lambda. The Lagrangian gives me a different way to write the objective function. I could write it as a max over lambda of the Lagrangian. So then my overall objective is to minimize that with respect to x. Now you might reasonably wonder, where did the constraints go here? That is, why does that max enforce the inequality constraints? To see why this works, let's imagine what would happen if one of the constraints was violated. It would mean that one of the fj's is greater than 0. When that happens, then a larger lambda results in a larger Lagrangian. That's because I'm adding the product of two positive numbers. If the constraint is satisfied, then I'm multiplying a positive number by either 0 or a negative number. But if a constraint is violated, then a larger lambda lets me make the Lagrangian as big as I want, and so that max runs off to infinity. But that's terrible for the minimum, so the min is never going to want to pick an x such that that max can run off to infinity. The effect of this is that there's an infinite penalty for violating one of the constraints, and so it never does it. So we've now convinced ourselves that the original problem can be viewed as the min over x of the max over lambdas of the Lagrangian. The concept of duality is to observe that the max-min inequality gives us a lower bound on this problem. After we flip them around, the inner part is now a min over x of the Lagrangian. And this is a thing that we want to maximize with respect to lambda. This is the dual problem in contrast to the original problem that we call the primal. So now we have these two related problems, the primal and the dual. Let's imagine that we look at the value after we solve each of these, and in the primal we get an f star, in the dual we get a d star. The duality gap is the difference between these two optima. It reflects the tightness of the lower bound provided on this problem by the max-min inequality. When strong duality holds, this gap is 0, and that's great because that means we get the same answer if we solve the primal or the dual. Convex duality holds in a convex optimization problem when it is strictly feasible. That is, when the feasible set contains at least one point for which not all constraints are active. And fortunately, this is a property that often holds for practical problems. One of the oldest and most important examples of convex optimization is the idea of linear programming. A quick note on terminology: programming in this context is just kind of an old school way to refer to optimization. In this video, I'm going to tell you about linear programming and just a bit about quadratic programming, and in reinforcement learning, one often talks about dynamic programming. These are just particular ways to think about optimization problems. Linear programming is kind of the granddaddy of convex optimization. It's incredibly widely used. It was invented back in the 40s, but it's still an active area of research. Basically, in a linear program, our objective function is just a linear weighting of the variables. You also have simple linear inequality constraints, and it's quite often to take the variable to need to be non-negative. This is just one way to write a linear program. There are a bunch of variations, some of which frame things as maxima and others that look at equality constraints. It's pretty straightforward to transform between the different varieties of linear programs. Although this looks like a really simple formalism, it turns out that there's a lot of different kinds of problems that can be turned into things that look like linear programs. For example, imagine that you're trying to come up with a diet. X might represent the non-negative quantities of different foods you might eat. You'd like to minimize how much money you're spending at Whole Foods, so you weight the different foods with their costs. But you also want to satisfy your recommended daily allowances of different nutrients, and so those provide constraints. You could apply a very similar logic to maximizing the output of a factory. The X's are the quantities of different items that you might produce. C reflects the profit that you get when you sell one of those items. And the constraints in A and B would reflect what materials are available to you. Another example is to think about how you might maximize network flow. The X's might be flows over individual links in a network. You might weight them in different ways depending on how important they are, but you want to maximize flow overall. Inequality constraints would represent different capacities. You might use equality constraints to represent the fact that each vertex needs to balance flow in with flow out. Finally, you could imagine setting up a linear program to help a farmer optimize what crops they're going to grow in their fields, subject to constraints in the land and also what, say, fertilizer they have available. I thought it'd be interesting to walk through an example that we can look at graphically. Let's imagine that there is a furniture maker who is making both tables and chairs to sell. She's trying to decide how many tables to build versus how many chairs to build. Let's say that she can sell a table for $200 and a chair for $40. Obviously, nice furniture costs a lot more than this, but let's go with it. Let's imagine that she has 45 hours in a week to work, and that a table takes 5 hours to make, and that a chair takes 2 hours to make. Now, I'm an amateur woodworker, and I can assure you that it takes me about 100 times longer than this, but let's imagine that she is super talented. Now, one of the concerns that our furniture maker has to consider is that customers always want chairs along with their table. In fact, they never want fewer than 4 chairs whenever they buy a table. Finally, tables are pretty big and the shop is pretty small, and so she can't hold more than 3 tables in storage at any one time. So let's set this up as a linear program. First, we're going to have variable x1 be the number of tables she can make per week, and x2 be the number of chairs she can make per week, and of course she can't make negative chairs, so these have non-negativity constraints. She's trying to maximize her revenue, and so she gets $200 every time she gets an x1 and $40 every time she does an x2. The total number of hours that she spends during the week has to be less than or equal to 45, and she has to make sure that she has enough chairs for every table she sells. Finally, she has to account for the fact that she can't make more than 3 tables in a week due to the size of her shop. So let's take a look at this graphically, where the x-axis is going to be the number of tables in a week and the y-axis is going to be the number of chairs in a week. We first plot the isocontours associated with revenue, so these are numbers that are getting bigger as you're going up and to the right. Now we incorporate the constraints, starting with the hour constraint. So any solution to this problem needs to be below the green line if she's going to spend 45 hours less in a week. Our second constraint is the fact that we need to make enough chairs for the tables, and so we need to be above the red line if we're going to have enough chairs. Finally, we have this hard constraint on the number of tables that corresponds to a vertical line that we have to be to the left of. These constraints give us a feasible region of possible solutions. And so we can maximize the revenue function subject to these constraints. Note, of course, that the feasible region is a convex set, and also that the global minimum is a vertex. It turns out that in a linear program, if there are any feasible points, then at least one of the global minima will be a vertex. Linear programming solvers are pretty far out of the scope of this video, but it's good to get a sort of general idea of how some of them work. The simplex algorithm is the oldest approach to solving a linear program, and it's still widely used. The basic approach starts at some feasible corner and then moves to the nearest best adjacent corner, and then stops when none of the neighboring corners are better. This greedy approach works because of the convexity of the problem. The downside of this strategy is that it's possible for there to be a very large number of neighboring corners when the problem gets large. So the worst case computational complexity of the simplex algorithm can be pretty bad. One algorithm that you hear quite a lot about is the ellipsoid method. This method is mostly about finding a feasible region, and the idea is that you start with a large ellipsoid that is guaranteed to contain the feasible region. Then you look in the middle of the ellipsoid and see whether or not it's feasible. If that point doesn't violate any of the constraints, then great, you're done. If you are violating the constraint, then you choose which half of the ellipse is the one that still contains the feasible region, and you create a new ellipse just for that half and recurse. This is a particularly appealing approach if the constraints are easy to evaluate. There are a bunch of other approaches that fall into the category of interior point methods. Interior point just refers to the idea that it doesn't stick on the boundaries of the convex polytope. Different approaches take different strategies. Some create things called barrier functions in order to represent the constraints, and others focus on the dual problem instead. And there are various hybrid approaches as well, and in fact this is an active area of research. I think it's worth taking a minute to look at the dual of a linear program. So here is our basic setup for an LP in which we have a linear weighting of the variables, inequality, and non-negativity constraints. We can follow our generic recipe from earlier and set up the Lagrangian. In this case, we have two kinds of Lagrange multipliers, lambda and nu reflecting the non-negativity constraints of x. As before, we can write this down as a primal, that is, as a min of a max, and we apply the min-max inequality to get our lower bound. Next, we think about what we would need to do to find the minimum with respect to x. We can do that by taking the gradient of the Lagrangian with respect to x, setting it to 0, and then solving. We notice that this gives us a constraint on lambda and nu in the dual. So now we have two kinds of problems. We have our original primal, and now we have this dual problem that we could also solve. And of course, you want to note in particular that this dual is also a linear program. I also want to draw your attention to the idea of a quadratic program. In a QP, we have an objective function that is quadratic in x, subject to linear constraints. Importantly, Q here in the quadratic is a positive definite matrix. Quadratic programs come up quite a lot in machine learning, in particular in support vector machines, or SVMs, but it also comes up in regression type problems where you're doing constrained least squares, and also in things like reinforcement learning where you might want to do model predictive control. To think about a quadratic program graphically, you first want to think about possibly having some kind of elongated bull represented by the objective function. Here are some isocontours to give you an idea of what that might look like in 2 dimensions. Then the constraints are a set of intersecting half spaces. Together, they form some kind of convex polytope that is imposed on top of the quadratic. Although this problem is still convex and relatively tractable, you can see that it's probably harder than the simple linear program because it's not obvious what direction you should go in. Quadratic programs generally also satisfy strong duality, and so it's useful to compute the dual. As usual, we start by writing down the Lagrangian. Then, of course, we apply the min-max inequality and focus on the inner piece where we're trying to figure out what we need to do to minimize the Lagrangian with respect to x. So we take the gradient of the Lagrangian with respect to x, set it to 0, and solve. Here, things are a little bit trickier than they were in the linear program in that we need to solve a linear system in order to find x. Nevertheless, we get it in closed form, and so we can substitute that value for x back into the Lagrangian. We do a little bit of tedious algebra, and we actually get another quadratic for the dual. So just like what happened with the linear program, when we find the dual of a quadratic program, we get another quadratic program, just now in terms of lambda. The reason that can be really interesting is because whereas the primal had n variables, the dual has m variables. That is, it has as many variables as there are constraints. There exist some problems where you have a lot more variables than you have constraints. So it's possible that this trick would make the problem quite a lot easier. In fact, when you use the kernelized version of the support vector machine, you take a problem that's infinite dimensional in the primal and turn it into a finite dimensional problem in the dual. So even though these things may look pretty technical and abstract, they really do come up in practical problems and even in introductory machine learning courses.